Our final project for CIS 563 physically based animation is to build an explosion simulation system. Explosions are very impressive special effects which are commonly used in many video games and feature films. However, explosions are extremely dangerous in real life, making computer graphics necessary to generate these effects. The goal of this project is to build a system to create realistic virtual explosions. The implementation is based on the paper titled Animating Suspended Particle Explosions by Feldman et al. This paper discusses an explosion framework where the fluid is combined with the particle system. The explosions are created due to interactions between these entities. The first component in our approach is to use a semi-Lagrangian fluid as the base framework. This fluid is modified to only be incompressible when no particles are present. This allows for particles to influence the divergence field of the fluid, producing the rapid gas expansion effect seen in an explosion. The standard fluid temperature advection equation is also modified to include additional terms which account for radiative heat loss into the environment and diffusive transfer of heat between the particles and the fluid. The second major component in the explosion system is the particle framework. All particles have a position, velocity, mass, temperature, and current status. A particle's status can be either normal, burning, or soot. When a particle is in the normal or burning state, its position is updated using the standard equations for acceleration. Its temperature is updated based on the heat transfer from the fluid. When a particle's temperature reaches a certain threshold, it ignites and begins burning. At this point, a portion of its mass is consumed each time step, and both heat and gaseous products are generated. Once all of a particle mass has been burned off, it is converted into a soot particle with a much smaller amount of mass and rendered in a different color.
The particle and fluid systems also have complex interactions. The particles are subjected to a drag force which moves them along with the fluid as it dissipates in the grid, and gravity. The particles also transfer heat and gaseous products into the fluid system. Finally, the fluid transfers heat into the particles, modifying their temperature and beginning the ignition process. Our explosion system is rendered using OpenGL and is written in C++. Eventually, we plan to transfer the simulation data into Maya for higher quality rendering. The code framework for the system is our smoke simulation assignment from earlier in the semester. Our progress to date includes implementation of the major framework components and interactions between the particles and fluid. Particles are correctly igniting and burning and travel along with the fluid velocity field. However, while each of the interactions is in place, anytime we attempt to modify the divergence field of the fluid, the PCG algorithm does not converge. Once this problem is solved, everything should function correctly. After explosions are replicated in OpenGL, we plan to transfer the data to Maya for higher quality renders. We also plan to convert the simulation into a Maya plugin for interactive control and ease of use. We now present some of our results. First, we have 10,000 particles igniting, burning, and turning into soot on a 10 by 10 by 1 grid. Next, we show a 20 by 20 by 1 grid with 100,000 particles where gravity is turned off to illustrate advection along the fluid velocity field. Finally, we present 100,000 particles on a 20 by 20 by 1 grid with gravitational force restored.